Welcome viewers to E-Pathasala, the course series for PG students of architecture. We were discussing about data structures in GIS. We have seen the various types of data, namely a vector and raster and its contents. Let us see about the coverage model. How do you have the details in a GIS structure? Because this will because it may not be directly impacting your understanding of GIS, but this will have an impact on when you are trying to work on your analysis part. So let us go to the coverage model. The model where how coverage will contain various aspects or the features in GIS. If I just look at this, you should understand that everything I was telling you, a point or a line or a data in your coverage in a given, say, a vector data, will contain the points, lines and areas which are otherwise nothing but your coordinates. And you also know what is an attribute information or the detail about that particular aspect, namely the point or line or area. Obviously, in a coverage model, you must be wondering how they are able to retrieve the data. So this is a graphical detail. This is a attribute detail which is stored as a table. How do you correlate them? How do you connect them? How do you retrieve the data? The data is done by, say, what is called as an identifier. As you can see here, the coverage is this, and this particular line, please you see here, this is represented as a line and it is connected with a node here, a vertex here and a node here. Obviously, its xy value here and xy value here are all stored in coordinate table. This is a table which cannot be accessed by the user. This is a system defined table. And the identifier here is that the value here is a 21. It could be any number. And for this particular line, this starting point, the middle point and the end point is stored as a XY pair. Obviously, when I am trying to go for the details about this line, namely the name of the road, type of road, maybe a state highway or your district highway or a national highway, whatever the type of road, or a simple mud road or whatever is that, the width of the road, length of the road, all the details, namely your attribute information about this road, have to be stored in an attribute table. This is visible to the user, and in fact we are the one who actually are developing that. So when I try to develop this, once I start digitizing this and I create this feature, it will have an ID, and that identification data or value cannot be changed or modified by your user. Obviously, how it gets connected from here to here, the coordinate table, again I told you, not visible to the user, only this is known to you. So this and this will be there, and it is connected with this directly, a unique identifier value or ID value 21. So this is how a coverage model works. Let us see how a point feature. As you know here, spatial location, X and Y, X axis and the Y axis, and the ID given to you is 82. As I was telling you, the point coordinate file is now translated from here to here. Obviously, this is the coordinate data. X value and the Y value will be stored here. When I retrieve the data, what the system does is, for this particular ID, an XY value will be plotted here in this X and Y. Obviously, when I prick here, its XY value is stored here. When I retrieve here, this XY value is retraced or retrieved and then put it back in the same position. So that's the beauty of that. Similarly, for this arc also, so you find that this is a various, I told you, various vertices which are there in between two nodes. The identifier of the arc is your 116, and obviously it consists of n number of pairs of your XY values, starting here, ending here with two more values. If you want a curved surface, obviously you have to have more number of values in between. Naturally, what will happen? You will have more number of values here. XY values, n number of values, many values will be present here, and retrieval automatically gets retrieved. Arc node topology, a very important aspect here. So when I have one single line, this is your arc, arc 1, and it starts from node F, that is 2, and then ending at 1. It goes like this, and obviously this will be the vertex. When I take the second arc, again it starts from 1 here, it goes along and ends up with 4. The from node, to node. The to node of your arc 1 will become the from node of the second arc. So this is your from node and this is your to node, and so on and so forth. What does the topology play here? You find that when I have here, this is an intersection. This particular line will split the arc 1 from 2. Otherwise what will happen? This would have been a continuous line. So when I have the topology aspect here, it not only takes into consideration this particular point, this is split here, and this will become a common point. That's what I want to insist upon. So when I'm storing the data, this particular data will have a pair of xy, and this will have xy. When I'm storing the data along with this line, what will happen? This will become a common point. Obviously, when I'm doing it for 5 and 2, this will become a common point. So what will happen? Naturally, I'll not have any redundancy of data. There will not be any repetition of data. This arc 1 will be 2 to 1, and arc 2 will be 1 to 4, and arc 5 will be 4 to 3. So this will be various nodes and its xy values. However, don't worry, whatever is the number of your vertices in between, every vertex will have its own xy value. So that will be stored. So this is what is your arc node topology. It will be building that, as I was telling you, overlapping or connecting cannot be possible unless it's got a node in between, and that will take care of the topological aspect. Polygon feature type. So in the previous case you just seen the lines part, and here this is a polygon, and it again you have the arc here, and this is your arc here, and it just goes like this, n number of vertex. And it, when I talk about the adjacent polygon, if I have one more polygon here, this particular line will be a common line to both of them. Of course, again you see here, there will not be any difficulty in storing that. One polygon 21, you have various vertices, and I have another polygon 116 somewhere here, and 145 somewhere here, and it will be. So what will the system do? It will say that for this particular 21, if I have 21 polygon ID 21, it is sharing the list of other arcs, namely 116 and 145. 116 may be here, 145 may be here, and it will share their values. Automatically the system will take care. When I am retrieving the data, it retrieves not only this polygon as such, it retrieves the common line and then draws for this particular polygon 116. And obviously for 116 polygon, what will be the common? 21 and 45. A part of it will be part of the line belonging to this particular polygon will be common to your 116 and 145, and so on and so forth. Then you have a very important aspect, namely the Polygon-Arc Topology. In the previous case, you have seen node-arc topology, remember? So now you are talking about your polygon and arc topology. So when I talk about this polygon, this is the polygon, isn't it? So it's arc topology. Naturally, for this particular polygon, you know that it starts from here, it goes like this, or it goes like this, in what form I have to digitize like this, or this particular arc might have been digitized like this, and a node is created here in this context for the polygon between 5. So just like your arc node topology, now here also in the case of your polygon arc topology, you find this is the way in which this is the polygon 6, and this will be the polygon 3 and 5, and so on and so forth. This will be the 5, and this will be 4 polygon, and you have one more polygon inside this polygon, that is your 2. They are not connected to each other, and 2 will be your entire polygon. Containment 4 will be within the polygon 2, and you see how it is. So we just go through these details, you will understand the same context of what you have seen in the earlier case. And obviously the most important aspect is that registering your satellite data or registering your map data to a particular coordinate system, you need what is called as a XY coordinates, nothing but your control points, which we otherwise called as a GCP, ground control points, and you have here. So this is one particular point, second point, third point, fourth point. Each and every value will be there. X tick, we otherwise call it as a tick value. X tick and Y value, and this is the ID value. ID for this 12, 13, 22, 23, 15 and so on and so forth. This 12 will have a X and Y value, and 13 will have X and Y value, and this will register the data to Earth coordinate system and it will display there. So we have the boundary feature type. Same context, I'm just given you in detail how boundary for this particular point. So any kind of a data will have the bounds. For example, even if it is non-regular shape, it will have a bound. The shape of the object may be non-regular in general, but you should remember that the shape, though it is non-regular in shape, it is bound by a rectangle or a square. So there is no other method of representing the data. So if I am representing the data, though I am seeing a polygon may be a regular shape or a non-regular shape, irrespective of its shape, it is bound by another aspect, namely your boundary. Though two polygons are adjacent to each other, its bounds are overlapping. That you have to bear in mind. For example, when I have another polygon here, the bounds of this polygon is this one. This arc is this one. You see here, this is one line, second line, third line. For this line, this may be your boundary. For this line, it may be here. For this line, it may be here. So the bounds are always overlapping with one another. Without that, because that is only to say that how the direction of that, because a simple method of representing data in a computer system. Annotation feature type. When I have annotation, you should remember that this annotation is also considered as a, say annotation nothing but labeling. Annotation is also considered as an object here in GIS. So you cannot label an object just like that. It has to contain a kind of a location. That's what I told you. A point data may be as a point data. It could be a discrete value as a point, or it could also be a annotation for an object. When an object is present, maybe your line data or your say your polygon data, it has to be understood. If somebody has to understand that, if it has to be understood, we'll have to have an annotation. That annotation is given as an object again. Please bear that in mind. So that is what we normally do. So here, when I'm looking at this polygon M21, A21, M21 and so on and so forth. So this one has also got a XY value, and that is shown as an object, and it is not a object which is something like in the case of your say CAD. CAD, you can never have a text file on the object itself. It has to be a separate entity. They'll have a separate layer. But in the case of GIS, it's not so. You can have the value within that polygon as an object that is also considered as an object, and it is having a value of XY. So that's what is your annotation feature type. Annotated arc you see here, and this is annotated polygon. And you can also describe whether you want to have parallel to the object or perpendicular to that. In any format, whatever you want, you can be showing them. Now coming back to the next important aspect. So you have seen that how the objects are positioned, how you take the XY value of each of them. Now you are going to see how they are stored. The more important thing, storage of your vector data. What is the file format, what you are supposed to follow? Of course, there are so many of them. Most of them have become obsolete, so I have not considered all of them. I have just taken only those which are very important. Storing of your vector data, or otherwise called as the file format of a vector data. It could be page description languages, PDLs. It could be vector information languages, namely as it is used in AutoCAD or MicroStation, DXF format or a DGN format. It also could be vector topological files, what we use in your GIS, GBF, DIME or Tiger. We will see the detail. These could be your vector data in other formats, namely non-Earth coordinate system. That is what is your AutoCAD and MicroStation. When it is non-Earth coordinate system, that is also vector data. You can't deny that, isn't it? So you'll have to have that. So when I'm bringing data from outside the world, namely your any of the surveyed data from AutoCAD or your MicroStation, you will have to remember that it will be to a non-Earth coordinate system. When it is non-earth coordinate system, though it is a vector data, it is not topologically related. So straight and simple. If a drawing is topologically related or it is referred to an earth coordinate system, it will become a map. That is a very, very vital aspect. So that's the second. Third one is I was telling you, the vector topological files which are meant exclusively for GIS. So these are what we normally use for your, say, in GIS. Of course, I was telling you about the page description languages or PDLs, which are more meant for, say, PostScript or your PDF, which are used more of a output as a printout rather than in GIS. So this one is your outputting as a PDF file. This is for non-earth coordinate system vector file, and this is your vector files which are used in GIS, GBF DIM. Now, coming back to your topological vector formats, GBF or DIM. We call it as the best known one is your geographic base file or GBF, dual independent map encoding model. That's what is a DIM model, GBF DIM model. And this one is a very interesting aspect. It will take into consideration various aspects which is very widely used in, say, what is called as your address matching or your street addresses. Normally we call it as address matching in GIS. Let us see that. What happens when one is supposed to locate oneself using your, say, a GIS model? You cannot be getting a XY location for each and every individual who is present based on the postal data. As all of you know pretty well that everywhere around the world we have details about a road and various households which are present, and when I want to reach a particular position, I use what is called as address. When I say address, I know it is, say, for example, 1 Fifth Avenue in a given terrain. So the Fifth Avenue will contain various buildings which are, how do you locate it? 1 and followed by the second number, third number, fourth number. Why I am using the word first number, third number? Because there is a variation. Initial stages previously, the numbering was given as 1, 2, 3, 4 on one side, followed by 5, 6, 7, 8 on the other side. Now, they have changed that concept, and now it is different. It is 1, 3, 5, 7, 9, that all the odd numbers on one side of the road, 2, 4, 6, 8, 10 on the other side of the road. So when I want to represent, it should be 1 for opposite 2, 3, 4, 5, 6. On either side of the road you have the numbering. It's an excellent method of numbering because accessing the data becomes much easier. Because when you have 1, 2, 3, 4, 5 on one side accounting to, say, 300 numbers, then followed by 301, if I want to access any data, it becomes very difficult. It's not impossible, it becomes difficult because storage becomes difficult. When I have all odd numbers 1, 2, 3, 1, 3, 5 on one side, 2, 4, obviously when I want to access the data, number 1, door number 1 and door number 3 or 2, it's very easy because it's exactly opposite. When I want to do something like, say, 1 and 45 and 2 and 48, again they are all close to one another. So that's the reason people now, the entire world, even in India, many cities, they have changed the numbering system. Now you have the numbering system, all odd numbers on one side, all even numbers on other side. So access becomes easy. That's what is your DIM and your GBF model, wherein which you get, and they are all linked, and we will see that in detail later. Of course, there is a difficulty here because there is a slight variation. When I have two intersecting roads, so what will happen? A major road will be going on, running, and suddenly I get an intersecting of another small road. So there will be a break in that date because that road cannot be a single road if I want to have an additional road, because you cannot expect in a given town or a city only one road, isn't it? You will have n number of roads. So the roads will be always running like this. So when there is a road running here, there will be an additional road which will be intersecting. At the time of intersecting will form a node. Then the road will be split into two. That main road will be split into two because it is intersected by another line. Obviously what will happen, the numbering system also will get affected because when the table will be affected in the sense. So for example, if it is intersecting somewhere around the 50th building, so 1 to 50 only will be in this arc and next to 51 will change there, isn't it? Of course, there will not be any effect as far as you are numbering, as far as you are numbering on 135. That will be there. 135 up to 49 in one direction, one side, and 2, 4, 6 up to 40, 50 will be in other road. Because otherwise it would have just continued up to 300, I was just telling you previously. So you will find that this sort of a variation or effect will also be there, but still it is a very effective system. And in all the cases, what we call is address matching. We will see that little later, the details. Address matching technique, where it is used in is a postal coding. So that's what is your GBF and your DIME system. You can see here, as you have here in this context, the road as such, this particular one, it's going like this. Because of the intersecting road rather, you have a node introduced here, 22. So what will happen when I want to represent this road? This will be split into two. 18 will be separate. Of course, let me take anywhere for that matter, what is given in the sample. Object 3 on the map, node 21. This is the node 21. So it just goes from 21 to 22. Then again, I'll have to start from 22 to 23. This road, either this road is getting affected by this road or this road is getting by affected, doesn't matter. I just want to give an example. So let me take this road and it is affected by this road at this junction. This is 22 node 22. So what will happen? This has to be split into two. See here, 21 to 22 and then again 22 to 23. So obviously when I'm storing the data, 21 to 22, what is that value? 88 to 90, and then on the high side it will be 1999 to 198. So this is what is the drawback, 1 or 2. So when I just try to split this into this, the numbers will get affected. Of course, it's not a big issue. I was telling you only the more number of nodes will be there. Numbers, sorry to say that, not exactly, numbers will not get affected. The number of arcs will be more because of the intersecting lines. This is what we use in your say GBF or your DIME method. Then very important method of storing your topological vector format, namely Tiger. This is what is very much in vogue now. Topologically integrated geographic encoding and referencing system, otherwise called as the Tiger. Here all the lines, points and areas can be explicitly addressed, unlike in the previous case. Topologically integrated. Because of the topological integration, you find here, this is how it just goes. It runs here E3, E4, and then of course doesn't matter here, E11 is coming here, and this is the way a polygon is represented, isn't it? We have already seen that arc 1, arc 2, arc 3 and so on and so forth. This Tiger topology follows. In address matching, if I want to find out, so here it is there, end node, the starting node of this particular line. So in this context, whatever is on the left side stored separately, whatever is on the right side stored separately. In the case of, I was telling you, the numbering 100 to 119 or 20, it could be more also. 101 to 119 is stored on this side, and 100 to 118 stored, that is even numbers and odd numbers. These are, of course, don't worry, missing numbers, just for representation's sake. 101, 5, 7, 13. 100, 2, 4, 6, 8, 10. It could be continuous or it could also be, there could be break different. So the Oak Avenue, the record, how does it there? So this will be the point, and this is the ID and the feature name Oak, and the type is an avenue. That's avenue, remember, road avenue they call it as. And the starting value 101 to 119 on the left side, 100 to 118 on the right side. So this is topologically integrated. So obviously, because of this context, it will be easy to store the data. So any kind of access, it has to just look at the number and the ID. So once the ID is there, automatically the system will retrieve the data and then display the data on the monitor, or it will be storing it elsewhere. So if you want to say 101 Oak Avenue, so obviously the system will look for Oak Avenue and the value or the number or whatever is that, and it will automatically correlate the value and retrieve the data from the system by going to, as you can see here, search time also becomes much easier, because I know that 101 I know it's a odd number. Obviously, I'll have to just check only in the left side. I will not bother to check at the right side. So that's a big advantage in your Tiger methodology. We have another method, namely the DLG, digital line graph. This is one method of storing the data. So this is has been developed by the United States Geological Survey, USGS, and they have produced a 7.5 minute by 15 minute topographic maps. This is more for your topographic maps, not for any other general large scale maps, more of a small scale map. You can see it has 7.5 minute by 15 minutes, very large scale, small scale rather. And it is available presently. This particular method is available for almost all the topographic maps of 7.5 minutes by 7.5 minutes. In India, we use a 5 minute by 5 minute. Different countries use different methods, and again that can also be subdivided into n number of divisions, and that could be your 15 seconds and so on and so forth, depending upon the scale. And it is separated into various layers. Fortunately, in United States, any kind of data pertaining to the government features, namely your state-related objects, either going to be hydrographic, that's the water objects, or it could be transportation road network. It is all available free of cost on the net. Any part of the country can be downloaded and used in your context. But of course, in India, we don't have. Different people have developed different methods, and it is all clashing. Each of them have followed the different methods, and it cannot be used as it is. But there is nothing like a federal data which is there in the case of your Indian context. Of course, in most of the foreign countries, federal data is available. You can use that. In addition to the topological data, namely the points, lines, and area, this will also contain what is called as the attribute code. So that's what is your important aspect here. And that will be a 3-digit major code and a 4-digit minor code. When you want to do something like a shoreline on the water body, I'm talking hydrographic data, and the shoreline will be always throughout the country will be represented as 050, 0200. So in any part of the country, when you find or where you find a hydrographic layer which contains a shoreline, it will be represented like this. Obviously, the file will have a header record for your metadata information. So that's what is your shoreline. You can see, for example, here note, you can see here 050 upper end of a stream and 050 001, and then once it is entering the stream water body, that is considered as, that is given a value of 4 node, and this is given 5, and so on and so forth. All the shoreline 200, 201 the man-made shoreline, any other line like a spring, like a flowing well. So when this sort of a common number is assigned, it becomes much easier for you to retrieve the data conveniently. Of course, when you talk about the network analysis, I was talking to you about your various aspects in vector data, especially the line data. Everything and anything is represented as a line, and that a closed line will become a polygon, and it will be covering an area. And that line itself is again consisting of your point data. Though we say that no object on the Earth's surface is a point or a line and an area, everything is an area. For representation and purposes, for kind of analysis purposes, we use line data. For example, when I am using the road network as, say for example, a road network which is used for various purposes, we call it as resources which are being transported. For anything like a bus, movement of a bus, I want to monitor the movement of a bus. I want to monitor the movement of vehicles in a given terrain. Then road is represented only as a line, and we give the various aspects to that line. For example, the direction of the road, the length of the road is already known because it is GIS. Then we'll have the flow direction, whether it's a single no entry or a single entry or a dual entry on both directions, whether it's going to be multiple lane or a single lane. All these aspects are there. So in such a case, this topology plays an important role, and the whole thing is otherwise called as network analysis. So the entire thing is built on, say, your topological models to establish routes between connected nodes. So this is what actually, and obviously the details are all stored in tables. So for all kinds of network analysis, we use roads as a line data. So with this, we will stop about the various aspects of your model in your coverage model, and that's the other things we have just seen, and finally we have seen the network. Thank you.